Well, you guys have made it. You made it past topic 3, which was our small section on extra derivative rules. You made it past topic 2, our main section on derivative rules. We finally get to our topic 4, applications of derivatives. So at this point, you should at least be somewhat comfortable with most of your derivative rules and definitely comfortable with the product, quotient, and chain rules. You're really going to just get practice on derivatives for the rest of this semester, and we still have, this is, late October. We still have about a month and a half left of just practicing those rules, practicing those rules. We're going to apply them in different ways, but to give you a quick rundown of this applications of derivatives section, I really split it into two pieces. The first part, which is going to be almost exactly half of this unit, is really all about better understanding graphs of functions. How do we apply derivatives to understand the shape of a graph, characteristics of a graph, so on and so forth. And then the second half is how else can derivatives help us maybe in real life, maybe to other real world problems, applications, or just doing regular everyday math a little bit more efficiently. So, opener. Your goal is to go through and define these four phrases. You'll notice that this says an absolute and then in parentheses global maximum. That's because these two words are used interchangeably. You'll hear something called an absolute maximum or a relative maximum. And then you'll also hear something called a global max or a local max. So giving you those colors to show which go together. They're just two different phrases. They mean the same thing, and your book uses them interchangeably, and so does the AP exam. So I try to use them interchangeably as well, just so you can get used to them. Your goal is to define them in the best way that you can. And now when you go through and define something, don't look up some complicated mathematical definition and write it down, unless you perfectly understand that, and then of course you're welcome to. I would suggest trying to find a way to put it in your own words, and maybe including a graph or an example of that too. So pause me, try to do these four phrases, please, using any resources you can, including your phone, internet, whatever sounds good, and then unpause when you're ready. All right, now I'm actually not going to define these four for you. We're really going to define all of these over the next couple of classes, and we're going to start pretty general, pretty layman's terms, and we're eventually going to build to some pretty good definitions, some using calculus, some not. But I think even if you're not quite sure what they mean, we'll at least get a good understanding of what they are, those relative or local, maximum, minimum, all that fun stuff by the end of this lesson. And we're just going to build on that over the next few lessons. So if you don't feel 100% confident, that's fine. Let's begin. The plural of maximum is strangely in math not maximums. It's actually maxima. So if someone says, find the maxima for the graph, it means there might be more than one maximum. And similar idea, the plural of minimum is minima. If we wanted to put these together, and instead of saying, please find the maxima and minima for this graph, these are actually known as extreme values. Extreme values, and it makes sense if you think of the highest and lowest values. The highest value maximum, lowest value minimum, those are the extreme values. And usually extreme values are shortened to extrema. So if they say find the extrema, then they really mean find all of these. Now, if you're asked to find the locations of the extrema, if someone said, where do these occur, then they're asking for the x-coordinate of that point. However, if the question asks you for the value of an extrema, then you need to give the y-coordinate. When in doubt, you can always give both, but if they ask for the value and you just give the x-coordinate, you will not get full credit for that problem. All right, let's do a little practice to make sure we understand what the heck these things are. Given the interval negative infinity to infinity, and remember intervals are always given along the x-axis, so they're telling us we're allowed to use any x value, identify the values of the global extrema on part A. Well, the global minimum is nothing too bad. So if I wanted to talk about and spell the global minimum, and I'll probably just write global min a little bit shorter. Notice up here I could have also said absolute min, and actually I tend to use absolute min a little bit more, but we'll practice. So the global min is the lowest the graph ever gets, and pretty much visually here, the lowest our graph ever gets seems to be -3. Right? They asked for the value, so I'm just giving the y value here. And then they asked for the global max as well. Well, the global max is the highest our graph ever gets, but our graph goes up infinitely far, doesn't it? That's what those arrows are for, and especially knowing what we do about this interval, it means the graph goes forever. There is no global max. We don't put infinity here. We just say does not exist. There is no global max. You are right in that it approaches positive infinity, but because infinity is not a number, we don't actually identify it as a value. We just say the value does not exist. All right, let's take a look at our second one. Given the intervals 0 to 2, and you might notice that this is actually a very similar graph to the one over here. It looks like it's just stopped, right? We could always put some arrows on the end, but we're just looking at a specific closed interval here. Identify the values of the absolute extrema. Similar question, though we used absolute instead of global, I think. Well, let's take a look. If I wanted to find the absolute max versus the absolute min, there's nothing too bad here. It looks like the largest, the highest this graph ever gets is a value of 4, and the lowest the graph ever gets is a value of 0. Cool. Easy peasy. Moving on. Given the interval, and notice now we are closed on one side and open on the other, inclusive and non-inclusive if you want, identify the locations and values of the global extrema. Well, let's start with the absolute max. That doesn't look like it's changed too much. Let's see. How about something like the absolute max occurs at x equals 2 and has a value of 4. Easy enough. Okay, what about the absolute min? Well, this one's a little bit trickier, I think, because we notice if I zoom in on this graph here that there's an open circle down here, which means there's no actual value here. This is an absence of value. So what happens is we have this point that's infinitely close there, which is infinitely close to 0, but not quite 0. But what is the closest point to 0? Well, we actually can't really put our finger on it. There is no official closest point to 0. Now, some of you might be very quick to recognize and say, ooh, we could talk about this in terms of limits. And you're right. You can talk about this in terms of limits. Remember, the limit of this graph as we approach 0 from the right side, as we're going this way, we'll call it f of x, is certainly 0. But I don't want the limit. The limit doesn't talk about what happens at the point, and the value talks about what happens at the point. There is no lowest point here. You're like, but yes, there is. The number that's right before this open circle, that's true. But because we can't actually give a value to that number, we accept that there is no absolute minimum. So we would just say something like, no absolute min occurs on the graph. Easy enough. Okay. And last but not least, given the open interval, so not including 0 or 2, identify the locations and values. Well, I bet you can see this one. They're both open here, so there is no highest nor a lowest value. And so there are no absolute extrema on this graph. Easy peasy. Well, hopefully you're getting a better idea of what it means to have an absolute max and absolute min, or global max and global min. So let's take it a step further. We want to see what has to happen to guarantee that a function has extreme values, specifically that it has an absolute max and absolute min. So looking up here, what seems to have to happen? Well, you'll notice that every time we were able to include an endpoint, right, any of these, there was certainly an absolute max. And when we didn't include an endpoint, there wasn't necessarily one. There was an absolute min here, even though there was nothing inclusive. They don't have to happen at the endpoints. But I think definitely looking at this, including the endpoint seems pretty darn important. In fact, every time we included an endpoint, there was an absolute max or a min. So in order to guarantee that a function has extreme values, the interval given for the function must be closed. Now again, don't confuse this. I'm just wanting to say, if I do this, do you know the function has an absolute max or an absolute min? And if it's closed, you do. However, does this function have an absolute max or absolute min? Certainly, it has an absolute min, and this is not closed. So just because we're guaranteeing something can happen doesn't mean that's the only way it can happen. I'm just saying if there's a closed interval, I know there is one, versus if there's an open interval, there could be one. Now let's go a step further, because is just having a closed interval enough to guarantee a global max and global min, to guarantee extreme values? Well, let's look at this guy. Closed interval, right? Very nice right here. Identify the values of the global extrema. Well, looking at this one, let's start with the absolute min. The absolute min here, right, and actually I should leave this blank before I'll fill it in a second. The absolute min here occurs both at x equals 0 and at x equals 1. There are actually absolute minima here. There are two, and that's okay. You can have more than one extreme value as long as it's the lowest one over the interval. And so the absolute minima here have a value of 0. Now, if this point was down here, then there'd only be one absolute min. There'd be an absolute minimum at -1. But because there's two lowest points, there are two absolute minima, but the value is still 0. All right, let's look at the absolute max. Uh-oh. No highest point again. There is no absolute max here. But we said closed interval. It shouldn't be guaranteed, and I don't think it should. So let's go ahead and take a look at this last one and see if we can really put this into words. Let's see. So we're looking for the absolute min and the absolute max. Well, let's see. Lowest point, that's down here. Absolute min is 1. Absolute max, not here because we get higher than that. Oh, no absolute max. So what broke down? How come not only having a closed interval, or how come having a closed interval didn't guarantee that there'd be extreme values, right? There was certainly a min on each of them, but there were no absolute maxes. So what else do we need to do? Well, in order to guarantee a function have both a maximum value and a minimum, and really it should say an absolute max and an absolute min, we actually have to look at a closed interval like we did before. And what's the issue here? Well, if I trace this, have to pick up my pen, trace this, have to pick up my pen, that is our beginner's definition of continuity. And so a function must be not only on a closed interval, but also continuous to guarantee that there are absolute maxes and mins. Again, it's very possible to have an open interval that has a max and min as well, but if you have a closed interval and the function's continuous, then I know without a doubt that there will be an absolute max and an absolute min. And this is all the extreme value theorem states. So this says extrema, which is awkward. So if we wanted to state this a little bit more rigorously, we'd say something like this. If f is continuous on the closed interval a to b, where have we seen that before? Isn't that the exact prefix for the intermediate value theorem? Right? For the intermediate value theorem to apply, we have to have f continuous on a closed interval. And it turns out that actually on really pretty much every single one of our theorems, we want f to be continuous on a closed interval. So that's never a bad way to start a theorem. If that happens, then what is guaranteed? Then f has at least, and notice that at least, right, we had two of these over here, has at least one absolute minimum and one absolute max. And we should also note that these extrema can be at the end points, right? So they can occur at the end points, like this guy was at the end point, okay? Or some location within the interval, right? This was a location within the interval, and that's allowed as well. Now, a few concluding notes here. A function can have absolute maxima and minima without those criteria. We've mentioned this, right? F of x equals sine of x is an open interval. Sine goes forever, very wavy. I always think of like a sea monster like that, right? It has an open interval, right? It goes from -infinity to infinity, but it has absolute maxes. It actually has an infinite number of absolute maxes, right? Doesn't it have these guys right here? The highest sine ever gets is 1. And it also has an infinite number of absolute mins. The lowest it ever gets is -1. So if we say, does sine of x have absolute maxes and mins? The answer is certainly yes. But can we say, does the extreme value theorem guarantee that sine has absolute maxes and mins? No, because if you're not looking on a closed interval, you can't apply the EVT. Last but not least, a function could also have a maximum value which is equal to a minimum value, right? For example, what if, and I'm just going to sketch a real tiny little graph here, what if I was looking Oops, that was not great. What if I was just looking at the function y equals 3, right? 1, 2, 3, and I went up to 4. So here's the function y equals 3, and we're going to restrict it from 1 to 4. So here's the function y equals 3. It goes from 1 to 4. This meets all the criteria of the extreme value theorem. Yeah, it's continuous, right? Y equals 3, you never have to pick up your pencil, and it's on a closed interval. As soon as we see those two, the extreme value theorem applies, which means there has to be a maximum, and in this case, the highest the graph ever gets on the y-axis is 3, and there has to be a minimum. The lowest the graph ever gets is also 3. So there are cases where the absolute min and max can be the same value. And this gives us a slightly more technical definition of the extreme value theorem. Same criteria for use. If f is continuous on a closed interval, then there exists numbers c and d such that f of c is greater than or equal to the entire function f of x, which in turn, should have done that in a different color, sorry, let's do it like this, which in turn is greater than or equal to f of d for all x. And I'm not sure if we've seen this before, this little sideways e thing. I guess it's not even sideways. This is our sign for element. So what we're saying is x is an element, meaning x is a value on the closed interval. That's a really nice way just to show what variable we're talking about on this closed interval. Right? If we're looking at this relationship then, we need to realize that f of c is greater than, so f of c is the largest value. So in this case, f of c is corresponding to the absolute maximum value. And f of d is the smallest, right? If you read backwards, it says f of d is less than f of x, or if you read forwards, f of x is greater than f of d. However, they're very careful to put equal signs all the way through, and that's because of this up above where the beginning or the smallest and the largest values can be equal to each other. Okay. At this point, you know 3 of the 5 theorems that you're expected to reference on the AP exam. So let's go ahead and compare those. So why don't you take a quick second, write down the names of each of them. If you remember the criteria for use, jot that down, and then see if you can put in your own words what they tell us. And the only thing we have left today is just do a quick short answer question, and that's all. So pause me, and then unpause me. And I'm back. Okay, squeeze theorem, IVT, EVT. Let's do the most recent one first. The EVT, that of course stands for the extreme value theorem, right? We just, not extrema, extreme value theorem. We'll abbreviate theorem so I don't have to screw up all the vowels in there. Criteria for use, continuous on a closed interval. And you could just say continuous on a closed interval. The nice part is that's the same thing for the IVT. Ha, we're cheating a bit. What it tells us, it's going to guarantee, you can practice your spelling, absolute max, and an absolute min. Cool. All right, what about the IVT? Well, the IVT is our intermediate, right? Intermediate level is the in-between level. It's the intermediate value theorem. What does it tell us? Well, it tells us, and this one is a little bit trickier here, because I would actually add on to the criteria of use first, but I'm going to use the space down below. If these are our endpoints for the x's, we actually need the y values. So it tells us that if we have f of a, and I'm going to leave a little space, and f of b, right? So those are the values of the endpoints, and these could be switched around depending on which one's bigger. And this is less than or equal to a value that we're interested in. I should call this f of r. Not sure why I decided to switch to a different function notation. That was silly, and now my pen doesn't want to erase. There we go. So it basically tells us if we find the y values of the endpoint, and they want to know, is there some value guaranteed on here, some y value? Well, as long as the y value is between the y values of the endpoints, then the answer is yes, this part is guaranteed, as long as our function is continuous on a closed interval and you have found these two endpoints. And the squeeze theorem, the lovely, lovely squeeze theorem. Well, what's the criteria for use? The criteria for use in this case is 2 things. First, we need to know that, and we're going to do three functions here, f of x has to be less than or equal to some function g of x, which is less than or equal to h of x. Basically, g of x, this whole function, has to be between f and h, right? If we have one function up here, that's our biggest function, and we have another function down here, and this is our smallest function, then g of x has to be hanging out in between those two. Okay? So not only does that have to happen, but also we need to have a limit, and this is going to be tough to fit in here, but we'll see what we can do. The limit as x approaches a of f of x has to be equal to the limit as x approaches a of h of x, meaning we need to know the limits of the two bounding functions, the function on the top and the function on the bottom, and those limits have to be equal. So if those two things have happened, this relationship and these limits equal, then we can conclude with our squeeze theorem. And the conclusion is that the limit as x approaches a of g of x is equal to both of those limits. Right? And that's actually pretty powerful, right? It's telling us that not only do we know the point is going to be in between, but also we know that the limit is going to be equal there as well. All right, let's try some applications. So I have a free response question that I created. I'm particularly proud of it. Well, maybe not that particularly proud, so let me know what mistakes I've made on here, because I'm sure I'll have to change a few things. There are 4 parts to it. Please go ahead, work it through. You should not really need a calculator for this. Eventually, you are going to have to plug some values in here, and you're definitely welcome to use a calculator on that part if you need help, but you should really practice. I mean, especially, let's say you have to plug -2 in here, you should really be able to do that by hand. It's definitely expected of you. I mean, I would say even if they asked you to plug 6 in here, you should be able to do that by hand. So just think on that. There are 4 parts to this, and we'll see what we can come up with. Go ahead and unpause when you're ready for me to go over it. Alrighty. Let's see. Part A. Is it guaranteed that f of x, where's f of x? F of x is the table up here. We're ignoring the equation. Has a maximum value over the interval -2 to 6. Justify your response. Well, a maximum value, what guarantees a max? Oh, that's our extreme value theorem. We just learned that. That's exciting. So a maximum value, well, I think 2 things have to happen. I think first, f of x has to be continuous. I don't see the word continuous anywhere up there. But wait, maybe they're trying to throw us off because I see twice differentiable. Twice differentiable means able to be, or you are able to take the derivative. The English language failed me there. And not only are you able to take the derivative, it's telling you the derivative exists not once but twice, which means not only can we find f prime of x, you can also take the derivative of that and find f double prime of x, and those derivatives will exist. Now, what does it mean if f is twice differentiable? Well, if something is differentiable, it means not only are there no sharp points on the graph, right? If my graph looked like that, that wouldn't be differentiable right here. But not only are there no sharp points, but I think also our graph is continuous, isn't it? I think one of the criteria to be differentiable is that your graph has to be continuous. So as soon as they tell us that f is twice differentiable, then we know that f is also continuous. But guess what? The graders don't. And so if you just put this as f of x is continuous on -2 to 6, then the extreme value theorem guarantees f of x must have a max value on the interval. You would not get full points. This actually almost verbatim came up last year on the intermediate value theorem. And they gave this same prefix. And I would say probably 80 or 90% of the people that answered the question knew that that prefix meant that f of x was continuous. But they didn't do a good job explaining it. And you do have to explain it. And so we can't even say something like differentiable and then draw an arrow and say continuous. It needs to be a little more specific than that. So we would say something like that, or something like this. You could say differentiability implies continuity. I would probably say as f of x is differentiable, then f of x is also continuous. That is a key phrase. They want to make sure that you understand that differentiability implies continuity. And so you need to connect differentiability to continuity. I would say 99% of people that I graded lost this first point on the IVT for not explaining why they knew the function was continuous. And then the rest is easy. There's no math we have to do. It's just knowing the definition of the EVT. All right, part B. Let h be a function defined as h of x equals g of x minus f of x. Oh my gosh, we already have two functions. Now we have a third one. Is h guaranteed to have an x-intercept on the interval -2 to 0? Guaranteed. This sounds like another theorem. This would make sense since I titled it my sweet theorem-based FRQ. Is h guaranteed to have an x-intercept? Well, let's see. X-intercepts. What do we remember about x-intercepts? I'll just sketch a cute little picture over here. I think x-intercept means we have some x value, it doesn't matter what, comma 0. So aren't they really asking, is there going to be an output of 0 on this interval? Or another way to think about it is, aren't they basically saying, is there some value, let's call the value r, since the AP exam seems to like to do that. They're basically saying, is there some value we can plug in here that will give us an answer, an output of 0? Well, this sounds like the IVT to me. I think if we found the value of h at -2 and the value of h at 0, as long as there's an output of 0, or as long as 0's output is between these two outputs, then I think we'll be fine. So here we go. We first need to find h of -2. And that is g of -2 minus f of -2, okay, equals, well, g of -2 definitely has a bit of work to it, right? It's this guy up here. So it's going to be, and I'm going to block it off in brackets so I remember that this is g of -2 here. It becomes 2 times -2 cubed minus -2 squared divided by 2 minus 2 by -2 plus 3 minus, and then f of -2, oh, that one's easier. F of -2 is just in the table. Ha! -10. Excellent. Okay, let's simplify this down. And again, you should really go through and do this math. It's not that hard. -2 cubed is -8 times another 2 is 16. Okay, 16, -2 squared is 4. 4 divided by 2 is 2. Plus 4 plus 3, and then 2 negatives make a positive here. So finishing this off, I think we have 16 plus 4 is 20, plus 3 is 23, plus 10 is 33, minus 2 is 31. I am going to check some of this at the end too, just to make sure I didn't screw anything up. But 20, 23, minus 2 is 21. That's what this guy is over here. Okay? And then we'll do the same thing with h of 0. And hopefully this one will be a little bit quicker. I think it will. So we have g of 0 minus f of 0. Okay, so g of 0 is just going to leave the 3 at the end, which is nice. And then f of 0 up here is 1. Cool. Like so. Okay, nothing too terrible. And then I think we just get 3 minus 1, which is 2. Well, let's see here. I definitely screwed something up already. I'm very proud of myself. Oh, I forgot a negative. That was so silly. -2 cubed is -8 times 2 is -16. Now, how did I know I screwed something up? Well, it's because I want 0 to be in between these two endpoints, and it was definitely not in between the two endpoints as I did this. So that was definitely silly on my part. Let's see how this changes things. This is -18 plus 7. -18 plus 7 is -11 plus 10. I'm getting -1 here. Does that sound better? And I'm going to, again, not cheat. I'm going to check my work over here. And I was still wrong. I should have gotten -11. So I am really just on a roll today. I'm very proud of myself. Always checking your work. Way to go. What did I do wrong this time? -2 cubed is -8 times 2 is -16. That is 4 divided by 2 is 2 minus 2 plus 4 plus 3. Oh, this is -11. I didn't get it wrong. I just forgot to include the plus 10. Okay, all right, I'm crushing it now. Here we go. Here we go for sure this time. -1 and 2 is 0 in between those two. It absolutely is. So let's finish this off. Okay. As h of x is continuous, And you can go over the top here and you can explain why h of x is continuous, right? H of x is made up of two continuous functions subtracting. Even going further, how do we know they're both continuous? Well, we already explained why f of x is continuous. You do not need to explain that again. Why is g of x continuous? Well, because that's just a polynomial and all polynomials are continuous. So again, the AP exam really doesn't have you explain why a function is continuous unless it's not obvious. This is considered obvious, this is not. So either way, as h of x is continuous, and, well, what else had to happen? These guys had to happen. And I always like to use the endpoints over here. So, and h of negative 2 is less than 0, which is less than h of 0, right? Then the IVT guarantees, and then we just have the writing. There will be an X-intercept on negative 2 to 0. Great. All right, part C. Find all values of x which cause g of x to have a horizontal tangent. Show any calculations leading to your conclusion. Well, okay, horizontal tangent. I think this is actually not a theorem. They actually want us to find the values, not guarantee the values. So let's get to it. For something to have a horizontal tangent, there's my horizontal tangent. That's a slope of 0. Slope? Oh, we should probably take the derivative. So let's start with g of x. I think g of x up here, 2x cubed. Let's move the screen like this. There we go. 2x cubed. I don't like this x squared divided by 2. I'm going to leave it as 1/2 x squared. I think students tend to be a little more comfortable with that. And then we, of course, need our derivative. So g prime of x, this becomes 6x squared minus 1x, 2 times 1/2, right, minus 2. You're going to find for this unit, as soon as you take the derivative, you are really going to want to simplify if it's easy to simplify. And in this case, when I say simplify, I mean factor, because eventually I'm going to want to be able to work with this equation, setting it equal to 0. We'll see that shortly. So let's get into our factoring. If you wanted to factor this, you can guess and check. You have two options. You have 6x and x, but you could also do 3x and 2x. Right? And you can play around with that for a bit. The nice part is the endpoint is either going to be -2, 2, -1, or 1. There's 4 possibilities here. But 4 times 2 gives us 8 different possibilities. You might dislike that, and this might actually be a good candidate to go through and do your factoring. So I'll remind you of one way you can factor if you didn't want to do that guess and check. You could say 6x squared and minus 2, right? I took these two guys, threw them in the box. And then the remaining spots in here are going to be taken up by this -1x. So I know the remaining spots better add to -1x, because when I put all this together, I want that to be the polynomial which we started with. Then, though, I also need to make sure that these two guys multiply to equal the multiplication of these two guys, which is -12x squared. Okay, now we can factor like normal. The question becomes, what multiplies to get -12 and adds up to get -1? I think that's got to be -4x and 3x. -4x and 3x, combining like terms gets us over here, looks good. So in the box we have -4x and 3x. Then we literally factor to find the exteriors, to find the outsides. So we say, well, what do 6x squared and 3x have in common? What's the greatest common factor? We can divide out of 3 and divide out an x. Once you have one of them, the rest is easy. 3x times what is 6x squared? Well, times 2x. 3x times what is 3x? That's times 1. 2x times what? -2. And we have our factors, 3x minus 2 and 2x plus 1. Again, you could have guessed and checked here, and honestly, depending on my stubbornness, I would have guessed and checked there, but totally up to you. Either way, there's our factoring. Let's go ahead and actually solve this problem. Find all values of x which would cause, moving around a bit, there we go, which would cause g of x to have a horizontal tangent. Well, horizontal tangents, we already said, occur when the slope is 0. This is the slope. This is the location the slopes occur at. So we need to set g prime of x equal to 0. I want to see when is the output of g prime 0, which means we're really setting 0, or we're really setting 3x minus 2 times 2x plus 1 equal to 0. What x value will cause the output to become 0? But that's easy enough. We just have two equations, like so. And I trust that you can solve these. Add 2, divide by 3. We get one x value. Subtract 1, divide by 2, and we get the other x value. There are two x values here, which cause g of x to have a horizontal tangent. That's 2/3 and -1/2. And those are the values because they cause the slope to become 0. All right, last problem. Here we go. It's known that k of x is another function. Oh my gosh, who designed this? It's known that k of x is a function which satisfies this property. F is below, g is above, on the interval from 1 to 3, and is defined for all values of x. Prove that k of x is continuous at x equals 2. Okay, well, one thing's kind of weird. The interval 1 to 3, there's nothing wrong with that for this function, but 1 to 3, that's like in here, we don't even have values from 1 to 3. We have no idea what these are. So what do we do with that? Well, the answer is nothing. It doesn't matter because we just want to talk about at x equals 2. 3 steps to proving something is continuous, right? The first step is we need to show that k of 2 actually exists, and we should probably find that value too. But we don't know anything else about the function k. Oh, but it's between here, isn't it? So we know that f of 2 has to be less than or equal to k of 2, which is less than or equal to g of 2. So I just replaced all the x's with the same x value because this relationship should hold for every x value because it tells us that k is defined for all values of x. There's no x value that when I plug in, k breaks. Okay, so cleaning this up a little bit, f of 2, well, let's see, f of 2 up here, oh, that's 13, that's not too bad, okay? So f of 2 is 13, that's less than or equal to k of 2. What about g of 2? Oh, we have to plug 2 in here. Let's just do some mental math, and I'll try not to screw it up too badly. 2 cubed is 8, times 2 is 16, right? 2 squared, 4 divided by 2 is 2. Minus 2 times 2 is 4 plus 3. So this to me looks like 19 minus 16. I'm sorry, 19 minus 6, which is 13. All right, so we know that g of 2 is 13. Well, if k of 2 is between a lower bound of 13 and an upper bound of 13, I'm pretty sure that that implies that k of 2 is 13. Easy enough. Okay, next up, k, get it? Next up, we have a limit, because in order for a function to be continuous, not only does there have to be a point there, we also need to find a limit there. So the limit as x approaches 2 of k of x. How do we find limits? Ugh, this one's kind of weird. Well, oh, wait. I have seen this set up before. I think if I can find these two limits and they're equal, then doesn't that mean the limit in the middle is existent and equal to both of those? Isn't that our squeeze theorem? So let's find each of the limits. The limit as x approaches 2 of g of x, I'll do that one first. That's the equation. And the reason I'm doing this first is because we just plugged 2 into this equation, and we got that the answer was 13. So I think I'm allowed to say that this is g of 2, which is 13. I think this middle step is very important because why are we actually allowed to plug 2 in here? Well, we're allowed to plug 2 in because g of x is continuous, which means that the limit has the same value as the point, and that's not always the case that those two are equal, right? We know g of x is continuous, and this eventually is the definition of continuity. Those two are equal to each other. In fact, that's what I'm going to do down here in step 3. I'm going to make sure that k of 2 is equal to the limit as x approaches 2 of k of x, basically making sure 1 is equal to 2. But since we know g is continuous, I know this is true. All right, that's good so far. The other thing that I'm going to need here, and I'm definitely going to run out of room, sorry, is the limit as x approaches 2 of f of x. And that is harder because I don't know what happens close to 2. I know what happens at 2, the value is 13, but I don't know what happens close to 2. Or do I? Because I think, didn't we also say that f is continuous, right? Here, and since f is continuous, doesn't that mean that the value at 2 is equal to what happens close to 2? And so I would probably put that over here. I would say this is equal to f of 2, which equals 13, and I would probably say because f of x is continuous. They tend to be a little nitpicky on using tables as limit values. They really want to make sure that you don't think this is always true. They want to make sure you know that's only true when f is continuous. Right? You could put this over here too because g of x is continuous. It's not going to hurt to put extra things that are correct. All right, well, we know both of these limits now. That's exciting. And we also know that this setup is true, so I think we can conclude quickly for 2. So I would say that, and I should have probably done this in a different color. Let's do, so it stands out. Let's do it in purple. The limit as x approaches 2 of k of x. So I would say something like, as the limit as x approaches 2 of g of x equals the limit as x approaches 2 of f of x, both equal 13, and f of x is less than or equal to h of x, which is less than or equal to g of x, then the squeeze theorem, there it is, squeeze theorem guarantees that the limit as x approaches 2 of k of x also equals 13. Sweet. Okay, so step 3. Is k of 2 equal to the limit as x approaches 2 of k of x? Yes, they're both equal to 13, so I'm going to put that at the end, 13. Therefore, k of x is continuous at x equals 2. Ta-da! Definitely a bit of work there, nothing terrible, but I was trying to really find a problem that we could work the squeeze theorem in just so we keep that fresh in your brain. Plus we got factoring, we got the IVT and the EVT. This is like a super theorem problem. I'll have to see if I can do another one once we learn our last 2 theorems and build them all together. So thank you as always for your hard work. Hopefully this wasn't too terrible of a day and got some nice review in. Extreme value theorem, very easy theorem. I would argue it's probably our least commonly referenced theorem, but you still need to know it. Good luck. Don't forget your independent practice.